let's talk about star clusters for now. So they're usually extremely useful, right? And first of all, stars are usually born in big groups. They're not born alone. And we're gonna talk about how stars are formed in the very next chapter. Uh, why are these star clusters extremely useful? Well, first of all, you get to study stars, all stars, at the same distance from us. So you're basically measuring the brightness, right? And it's going to be not going to be, you have the relative brightness of the members of the group is not going to be dependent on how far away from each other they are. They're basically the same distance from us, right? So luminosity scales very well with the brightness, right? So this is intrinsic to the stars, and this is what we measure. Okay, so basically you look in a cluster and you see stars that are brighter than others. Well, they're intrinsically brighter than others, right? Because the distance is not going to affect the relative brightness of the stars. Also, the other very important thing about stars in a star cluster is that they all have the same age. They formed at the same time. And of the same material. So they have the same composition. And so the only thing that varies from star to star is their mass. And that's important because the mass, stellar mass, determines their fate. Remember? High mass stars, we say they die quickly. Man. Low mass stars live very long lives, right? The high mass stars, kind of like rock stars, long, boring lives would characterize the low mass stars. So anyway, star clusters, there are two types. So let's talk about them. Let's see what kinds of clusters, star clusters are out there. So one, that is the open cluster, and that usually has just a few thousand loosely packed stars. So this is, for example, an image of the Pleiades or the Subaru or the Seven Sisters. So these are other names for, obviously this is in Japanese. So that probably explains to you the sign for the Subaru cars as well. It's actually coming exactly from how this open cluster, right? You don't see here a few thousand stars loosely packed. You only see the brightest stars. They're actually so bright and so hot, brightest, hot, very young stars. Okay, they're so bright that they outshine basically the rest of the cluster. So that's one type, and the other type is the globular clusters, and those are made up of a few million, at least 1 million of stars, and they're densely packed in together by gravity, and they are very old. So these are places where the only places where we can find old stars. These things have lived for basically the age of the universe, and I'll tell you in a second how we figured that out. Okay, so now you remember that HR diagram, or Hertzsprung-Russell diagram, or we also call it a color magnitude diagram, or the CMD. Okay, where we have luminosity on the y-axis, or brightness, or power per unit area, and we have the temperature on the x-axis, or color, right? It goes from blue to red, and also the spectral type. Look at that. The O, B, A, F, G, K, M. So look at that. Our sun, it has the G type, spectral type, so a temperature of about 6,000 Kelvin, and it's kind of yellow in color, and its brightness is 1 solar luminosity. Okay, all the other ones above this are going to be higher luminosity than the sun, and below it's going to be lower luminosity than the sun. And you recognize here maybe the main sequence, and then some places here where we have the giants, and then the supergiants. The horizontal branch would be here. Okay, so we have the sub-giant branch around here, and then the white dwarfs, where Sirius B and Procyon B, some examples of white dwarfs out there you might have heard of. Okay, so we also have some examples here of other stars and where they are in diagrams like this, basically in terms of their color or temperature or spectral type and their luminosity. Okay, so here's what happens. So a cluster is born. It's not going to have the giants when it's born. Okay, it's going to have just the main sequence, right? So the star is born, and it's going to be having some properties that correspond to the main sequence. And then what's happening? Then we have the high mass stars, who live for very short times, right? Look at that, lifetimes, just 10 million years. Just, of course, we're talking about astronomical times here. And we have the low mass stars, that kind of live forever. So look at this lifetime. So they're gonna live expected to live based on how they churn that hydrogen into helium in their core. It's live for 10 to the 11 years. So what is that? 10 to the 9 is a billion, so a few hundreds of billions of years. This is longer than the age of the universe. You probably recall from the very first chapter that the universe is just 14 billion years old. Okay, so you know these stars might have formed at the beginning of the universe, maybe, okay? And they're gonna live pretty much forever, right? So we're gonna find these kind of stars in every cluster that we're going to look for. Okay, so now here's what happens: as the time goes by, we end up with these stars. You know, they're going to be erased. They're not going to exist. They're not going to exist on this main sequence because they're going to die and they're going to become these supergiants. Okay, and so basically, by the time the cluster lived for 10 to the 7 years or 10 million years, right? These stars are going to basically start exploding as supernovae and not exist on the main sequence as star. And so the main sequence is going to be kind of cut. There is going to be a cut in the main sequence. No more stars. Here after 10 million years. And then you keep going after 100 million years, okay? You're gonna lose all of these stars and you're left with stars like Vega, Sirius, right? And then for another 10 times the 10 million years, so that's going to be now we have 100 and then 1,000 million years, so we're getting to 1 giga year, a few giga years, like the sun that lived for 5 giga years, right? There are the clusters of stars. They're not going to show those stars on the main sequence anymore. So here are some. For example, the Pleiades. This is actually, as I probably mentioned, a young star cluster. And it's young because it still shows stars that are of type B, okay? Stars that lived for about 100 million years, right? So young, about 100 million years. Okay, so you see all the other stars here, right? But the ones that lived for less than 100 million years, they're not on the main sequence anymore. They went through the giant phase, they went through the horizontal branch, and there are maybe some white dwarfs left behind. Actually, the high mass stars don't go through that sequence as we will see in the next chapters. They exploded as supernovae, left behind some neutron stars or black holes, right? So not on this very young cluster, but example of how other types of clusters look like. So we have here 4 plotted in this diagram in terms of luminosity and the temperature, right? The main sequence for 4 clusters. And look at the Persei clusters. This cluster presents very hot O and B type stars, okay, but also some giants associated with them. All the other stars are actually going to be very difficult to observe because these are very, very luminous. However, when we look again at the Pleiades, we looked before at the Pleiades, right? So those would be the Pleiades. You see there is no star younger than 100 million years. All right, there are all the other ones on the main sequence, but these younger, like the O stars, they disappeared, they died, they do not exist, they cannot be observed in this cluster. Let's look at the Hyades. You see, for the Hyades, there is a turning point here. Turning point in the main sequence, above which there are no more stars. So basically, there are no stars that are younger than 10 to the 9 or 1,000 million years, or a 1 giga year. Okay, there is only stars that are going to continue to live for longer. So what happened? Those stars lost their fuel in their center. It was all converted into helium, and other things happened to the star. Okay, some of them became, look at them, subgiants, right? And eventually they become, most of them, they will start becoming the white dwarfs. And now look for comparison at another cluster, the NGC 188, right? So the yellow symbols, these ones. And you see the turning point here in the main sequence is even lower in the sequence. That means there are no stars that are younger than 10 giga years, right? So this is 10 giga years. So this basically has lived for that long, right? So we can tell from the main sequence turn off point, what is the age of the cluster, right? So you put together the main sequence, you basically observe for all the stars that you can distinguish or resolve in that cluster of stars. You measure the luminosity and their temperature, put together the HR diagram, look at the main sequence and see where it stops, where it has the turn off point in the main sequence, and that is going to tell us the age. And we can obviously do that by comparing with some models. We have some ideas as to what happens in the interior of the stars, and we can model that and put a number actually to those ages. So we can tell, for example, how old are the oldest globular clusters that we observe out there in the sky, and we see that they're actually pretty old. So remember, universe, it's about 14 billion or giga years old. So some globular clusters have stars like, with masses smaller than the mass of the sun, that are at least 13 billion years old.